So I welcome everyone to this afternoon. I'm sure we will have an exciting talk by Herbert. I'm really happy that you can give this presentation. I think everyone in system security knows Herbert's research, or the research his group does in Amsterdam. And some of you might also know the textbook that he's working on operating systems, and it's been interesting for me because I teach class on operating systems for the first time now. So I really come to appreciate not just the research papers that we all know, but also the operating systems textbook. Herbert also, there's lots of research going on, but in particular in reversing, and there's also, he also had an ESC grant on this topic, and actually one of our PhD students at TU Wien and SBA Research joined the group, and he really enjoys working on security and operating systems. And so I'm very happy that we have this presentation on attacks on the Linux kernel today.
All right. Thank you for the introduction. Let me just say that there's actually a new edition of the book coming out, as I mentioned earlier. So stay tuned. It should have a lot more interesting information, up-to-date information about the security. Also, you know, amongst others, these transient execution attacks feature prominently in there now. Okay, so as mentioned, I'm from the VUSEC System Security Research Group at Vrije Universiteit Amsterdam, where we do a lot of work on attacks but also just as much on defenses, perhaps more even. But today I'm going to talk about an attack, blind attacks, and in particular blind attacks on the Linux kernel. And when I say a blind attack, what I mean is an attack where the attacker doesn't know too much about the victim, the memory layout, or lots of other things. And the Linux kernel is then a particularly challenging target. Now, this presentation is going to be perhaps different from some other presentations in the series. I'm not sure. It will be technical. It will be a little bit low level. But I think there are some really interesting high-level lessons to learn from this particular attack that I'm going to discuss. And I will try to handhold you through a number of steps in the approach, so that it should be accessible, hopefully, even if you're not an expert in this area. Okay, so the main high-level lessons that I want to point out are essentially this, right? So that attackers can take magic from different areas, from hardware and from software, vulnerabilities in the hardware, vulnerabilities in the software, and combine them and create something that is very powerful. Not only that, but also we are not geared out to deal with these kind of combinations of attacks, because it requires defenses that also look beyond their own expertise and their own scope, right? So if you're very good at memory safety, for instance, you don't necessarily think about some of the other things in hardware vulnerabilities and how these things can be combined. And I'll show you an example of that. That is the goal that we have today. And like I said, I want to do this in a couple of relatively easy steps. And the first step is just a reminder of how traditional attacks work. They may no longer work today, but this is how we used to exploit systems. And just to sketch some of the context, the work that I'm going to be presenting, the blind attacks, has been inspired by the blind ROP attacks by the late Andrea Bitao and his colleagues at Stanford. Really cool work. So if you're familiar with that work, you'll recognize some of these slides that I've just simply copied or recreated, and you may recognize this simple example, which is a trivially vulnerable program. Okay, it's a server program that accepts data from the network and reads it into a buffer that has 1024 bytes and doesn't check whether or not these bytes actually fit in the buffer. Okay, so if the attacker provides more than 1024 bytes, they will overflow the buffer and overwrite whatever is adjacent to it in memory. For instance, it may overwrite the return address. Say we fill the buffer with capital A's, capital A in ASCII is hex 41. We overwrite the return address with this value. And I'd like to ask people to mute their microphones. There's actually a little bit of noise in the background. Thank you. So you overwrite the return address, and that means that if the function returns here, it will crash the program, right? And that's bad, but it's not really what the attacker wants to do. What the attacker wants to do is maybe get a shell on the victim machine. So what the attacker would like to do is not crash, but rather execute little snippets of code from the binary such that the attacker gets a shell. For instance, maybe the attacker wants to do a .to system call that connects the network connection, the socket that the attacker has with standard in and also with standard out, and then do an exec of the shell. So you actually execute the shell. Let's say these snippets of code are what the attacker wants to execute. So if these snippets of code exist in the binary that you're attacking, what the attacker can do is simply provide the addresses of these snippets of code on the stack. The first address here is 8,000. So the program on the return will execute this instruction, this code here, and then do a return, look for a return address on the stack again, find 6,000 there. So it will execute this snippet of code and then do another return, find the address 7,000 on the stack and start executing the exact VE, and then the attacker has a shell. Now, this is a hugely simplified but almost realistic explanation of how an attack works. But now, of course, the trouble is, and this is probably something that you observe immediately, that the attacker needs to know exactly the addresses of these snippets of code. And by now, you're probably saying, that's no longer possible because we have address space layout randomization. Okay, so the memory layout has been randomized. And when we say address space layout randomization today, it means either coarse-grained address space layout randomization or increasingly fine-grained address space layout randomization. And the difference is simply that with coarse-grained address space layout randomization, you randomize the base of, say, the code segment or the base of the heap or the base of the stack, but you do not randomize whatever is in the code segment relative to that base. And with fine-grained address space layout randomization, you do not just randomize the base, right? But you do not just start at a random offset, but you also randomize everything relative to that base. So functions may be at different locations in the code segment, or basic blocks, or maybe pages may be randomized, some fine-grained address space layout randomization. This is coming to the Linux kernel pretty soon now, and the expectations are fairly high. This is Kees Cook, who's security engineer responsible for security in the kernel. And he announces this and says, this will strongly diminish some of the things that an attacker is able to do. Well, let's see about that. Let's first take a step back, though, and summarize what we've learned. What an attacker needs to do nowadays to attack a system is to break address space layout randomization. Okay, that's one thing. And the other thing that he needs to do is to find these snippets of code in the binary. Okay, so that he can stitch them together with these return addresses. But this only works if you can do this, if you can have a look at these gadgets, if you can break address space layout randomization. And it may be the case that you're attacking a remote server and you don't even have the binary, for instance. And that brings us to part 2, where we're going to talk about these blind attacks. Okay. Blind attacks on a remote server. And this is, as mentioned, work by the late Andrea Bitao and his colleagues at Stanford, who published a paper called Hacking Blind a couple of years ago. And what they show, and this is super cool, is that you can attack a remote server, at least some remote servers, even if you don't know what the memory layout of that server is, you don't know the source of that server, you don't know the binary, perhaps even, you don't even know what code is in that server. You can still exploit that server. And this is known as blind return-oriented programming, or blind drop. And the recipe for blind drop is roughly the same as what we saw earlier, with an additional step. So we still need to break address space layout randomization, but now we need to do this remotely. And since we don't have the binary anymore, that's what we said, we don't know what we're attacking, we're completely blind. We instead try to exploit the remote program just enough, with just a little bit of exploitation, so that we can call a write library call, and therefore a write system call, so that we can dump the content of memory of the victim across the network on a socket to the attacker, so the attacker can piece together the binary again, and then look for the gadgets, and then look for where these gadgets are, and launch the traditional exploit. Okay. Now, how can you do this? Well, it's a tricky thing, and it only works on particular servers. Okay, it requires the servers to be crash resistant in a particular way, which is true for some servers, but certainly not for all, and certainly not for many programs. But Nginx, for instance, might be a good example, where you have a web server that starts up and then forks a number of worker processes, that, so child processes that take care of the communication with the clients. Okay, and if one of the child processes crashes, that's perfectly fine. For instance, there's a bug or so, that's perfectly fine, because the server will notice this and will simply fork a new process. Okay, so that's good for reliability. These servers simply keep running even if there are crashes. Okay, and since this is a fork system call, and a fork system call will simply start a new process with the exact same address space, the exact same memory layout as the parent process, all of these processes have the same address space layout. So we can, as an attacker, probe around and see if we can break the address space layout randomization of one process. And it doesn't matter if we crash many processes in the while doing this, because it will simply keep forking, and we can keep trying, and they will all have the same layout. In fact, what the authors did was use this crash as a side channel to learn to infer what was happening on the server side. Normally, when you send a request to a server, you get a reply back and everything is fine. Okay, but if we, just like in the example that I showed earlier, overflow our buffer with all capital A's, this will crash the Nginx server, and it will lead to a connection that is terminated. Okay, so this is something, and that's the signal that they use, that you can observe as an attacker. You can observe that the connection terminated, the connection closed. Okay, it's a very coarse and crude side channel, and the question is what you can do with it. Well, the simplest thing that you can do is simply try, right? You could simply, here's the buffer again, we can overwrite the return address with a bunch of tries. For instance, we've tried this address, and guess what? It led to a crash. We can try another address, and guess what? It led to a crash again. And we can keep doing this until the cows come home, but it takes a long time before we actually do something that is directly useful. But what we can do is keep doing it until we find some code that at least is not a crash. So at some point, we're going to find some code that doesn't crash, but simply hangs the connection, right? This may be because the instructions here are doing a sleep or a blocking read or some other blocking call. Whatever the reason may be, it leads to a hang. And that means that the connection doesn't terminate. For once, the connection hangs and doesn't terminate. It's different behavior. All the other places crash. So this is a very crude side channel. You can distinguish between two snippets of code, one that crashes and one that does God knows what, but at least it doesn't crash. And what we want, and this is just going to be the intuition of what the attackers did, we want to have some fine-grained control. For instance, we want to control some registers. Okay, you maybe want to do a lot of other things. I'm just going to sketch one fine-grained thing that you could do with this. Say you want to control a bunch of registers, and wouldn't it be nice if you could find some snippet of code in the target binary, in the victim binary, that looked like this. Okay, so we have 6 pop instructions in a row that pop a value of the stack and write it into a register, and then we execute a return instruction. Okay, this would be really nice if you could find this as an attacker, because then you control all the values in these registers, because we had this vulnerability on the stack. We could overwrite values on the stack. And so if we are able to execute this code, we immediately could control 6 registers. Now, the good thing about this so-called BROC gadget is that it's a very common gadget, right? Because, and why is it a common gadget? Well, all of these registers are so-called callee saved. So when you do a function call, the callee will push all of these values of the register on the stack, and just before it returns, it will pop them off the stack again to restore them. Okay, so it's very common to have this code in a program. So it's very common. We would like to have it as an attacker. But the question is, how do we find something that is so fine-grained as that? 7 instructions, 7 particular instructions. How do we find that in a remote binary? Well, what we did so far was simply blindly probe around, and we found only 2 things. We found gadgets, so snippets of code that crashed, and we found one particular gadget, one particular snippet of code that did not crash. It just hung the process, hung the connection. So how can we go from this to finding that? Well, we're simply going to do what we did earlier, and that is overwrite the buffer, find some probe address for the return address to try different locations. But we want to be able to tell whether or not we've executed this code. Okay, and we do that by adding a little bit more on the stack. And in particular, what we do is we add 6 crash instructions. So addresses of crash gadgets on the stack, and 1 address of a stop gadget, which doesn't crash but hangs. So now we can detect exactly that this code is executed, because only if we execute code like this, and that's a very particular signature, we will actually pop all of these values off the stack. All of these addresses of crash gadgets will be popped off the stack. And then there is a return, which will return to the stop gadget, so which does not crash. So only if your target instruction that you put in the probe here executed here, you would get some behavior that led to a hang. In all probability, it's very unlikely to have other code that exhibits this behavior. Okay, if you tried a different probe, say you tried, by accident, you tried to execute from this instruction here, you would pop 4 values of the stack, and the next instruction that you tried to return to was a crash instruction, so you'd crash. Anyway, this is a side channel that allows you to find, so if your connection hangs, it allows you to determine that that address that you put there must have been something like this gadget, and you control a lot of registers in one go. I don't want to say much more about this. There's a lot more that you need to do. You need to control more registers. You need to control other registers. You need to find functions. You need to dump the contents of memory across the socket and find more gadgets and all of these things. But that's not our work. I don't want to talk about this. I just want to give you the intuition that with this very crude side channel, you can find very fine-grained information. Okay. There are major drawbacks, unfortunately, in these blind drop attacks. And one of them is that you need thousands of crashes before you can do this, right? And that's super noisy, right? So it relies on the fact that there's no intrusion detection system or system administrator that will investigate what's going on if you have thousands of crashes in a row. And moreover, it requires the victim software, the target software, to tolerate so many crashes to begin with. Okay, and like I said, this is true for some servers, but it's definitely not true for software in general. And it's also certainly not true for some of the most, high-value targets that exist, such as the Linux kernel, right? If you crash the Linux kernel only once as an attacker, it's game over, right? The system is down, it's all over. Okay, so you cannot afford any crashes. So that's bad. But now the world has changed, right? So since 2018, we all know about these new vulnerabilities in hardware, Spectre and Meltdown, okay? And these Spectre and Meltdown attacks allow you to leak a lot of interesting information. Can we somehow combine these two vulnerabilities, the hardware and software vulnerabilities, such that that we perhaps can bypass these issues, these problems? And in case you don't know the details of Spectre, or you've forgotten the details of Spectre, let me just do a very brief recap. Spectre is a vulnerability, a speculative execution vulnerability that has many variants, and I'm just sketching two of the best known variants on this slide, Spectre variant 1 and Spectre variant 2. And they both rely on the fact that the CPU tries to optimize things such that it does not need to wait, okay, if it can avoid it. Okay. For instance, here we have a snippet of code where the program wants to do an access of an array element where the index is user provided, so it's untrusted. So it could have been provided by an attacker. And the code is doing the right thing. It's checking whether or not the index is in bounds. And only if the index is in bounds, it will read this array element, put it in data, and use data as an index in a second array. Okay. Now, this may take a long time to resolve, right? So the outcome of the condition may take a long time to resolve, for instance, because one of the elements is not in the cache, needs to be fetched from memory, takes a long time. And the CPU decides, I really don't want to wait, that takes too long. So instead, it will speculate on the outcome of this condition. It will try to predict the most likely outcome. Okay? And if the last 100 times the index was in bounds, the CPU is going to say, well, it's probably going to be in bounds again. Let me just execute this code speculatively. Okay. Of course, it may have misspeculated, and in that case, it needs to undo the effects of this code, all the architecturally visible effects of that code. But that's fine. It will deal with it, and it will then continue executing at the right instruction. The problem here is that, oh, and by the way, here we have something similar. We have an indirect branch, in this case, an indirect call, where the code is calling some function that is computed by the program, and the CPU is going to do the same thing. If the last few times it tried to call function foo, the CPU is going to assume that it's going to call foo again. Okay. The problem here is twofold. So first of all, the attacker can force the misprediction, right? The attacker can simply provide an index that is in bounds 100 times in a row, and then provide an index that is out of bounds. Okay, that will force the execution, the speculative execution of these instructions. Okay. These instructions will be executed speculatively, and if the 101st time was an index that was out of bounds, it will access speculatively only some memory location that you're not supposed to access. Okay, so you're accessing secret data. Okay. The second problem is that, yes, these speculative execution instructions are undone in the sense of all the architecturally visible effects are no longer there, but there are still effects visible at the microarchitecture, so the level where you implement the architecture. Okay, for instance, in the cache. Let's have a look at what that may look like. And for simplicity's sake, just for the explanation, I'm going to assume that this array 2 is shared between the victim and the attacker, say the kernel and the user process. It's not a requirement, it just makes the explanation a little bit easier. Okay. What the attacker is going to do is make sure that all of the elements of this array are not cached, are not in a cache. You just access a lot of other data, so the cache is used for other stuff. And that means that if the attacker were to access any of these elements in the array, the accesses would all be very slow, okay, because it needs to be fetched from main memory. Okay. Now, the other thing that the attacker does is provide, say, 100 times an index that is in bounds, and the 101st time, the attacker provides a value that is out of bounds. So this code will be executed speculatively using an index that is out of bounds that reads some secret data. Say it reads the value 2, a byte value that has a value 2. Okay, that byte will then be used as an index in this array 2. Okay, the CPU is going to discover that it got it wrong, it mispredicted, and it should have not executed this code, so it will undo all the architecturally visible effects. But what has happened for this array access with the index 2 is that some data was loaded from main memory into the cache, and that is not undone. Okay, so that means that if the attacker now starts executing all the elements in the array, all of the elements will be slow because they need to be fetched from main memory, except one, which is really fast because it was already in the cache. So the attacker now knows the index, that the array element at index 2 was really fast. So the value that was used as an index here and that was therefore obtained from this access here must have been the value 2. Okay, so that's really devastatingly bad, but fortunately nowadays there are so many Spectre mitigations that pulling off such an attack, certainly on the Linux kernel, is really difficult. We have software mitigations such as red pollines, we have hardware mitigations, we have kernel developers that have scrutinized the Linux kernel code and looked at some of the constructs that were there and said, oops, this looks dangerous, let me just protect this. And nowadays, doing a Spectre attack on the Linux kernel was believed to be extremely, extremely difficult. At the same time, the blind attacks that we saw earlier on these Nginx server and some other web servers are also super difficult and also only apply to particular code that is crash resistant in the way that I described. And it's certainly not possible on the Linux kernel. Like I said, there's fine-grained randomization in the kernel soon, and any guess that is wrong in the Linux kernel will lead to a system crash, so it's fatal. So blind attacks on the Linux kernel were also thought to be impractical. But what if we combine these two things? What if we combine these traditional software vulnerabilities and software exploits with hardware vulnerabilities and hardware exploits? Okay. Maybe we can now bypass some of these defenses. And that brings me to part 4, which is the part where we combine Spectre with traditional software attacks and bypass all of the security mechanisms in the Linux kernel. So the combination of Spectre and traditional old school software exploitation is what I call symbiotic, in the sense that unlike previous things where you had to do one thing to obtain something and break address space layout randomization and then use that to do the next step, here we have something new where both of these things, so the Spectre side and the traditional software exploitation, make each other stronger. So software exploitation, as we shall see, generalize Spectre attacks. In other words, they make Spectre attacks possible in situations where they previously were not possible. And similarly, the Spectre vulnerability generalizes software exploits, making software exploits possible in this blind fashion where they were previously not vulnerable. So the combination of these two things, Spectre and software exploitation, is greater than the sum of its parts. Okay. And the main trick that we're using is that we do not try to use poisoning of the branch predictor to have the code execute some instructions at a location that the attacker controls. We do not mess with the branch predictor for that reason at all. In fact, what we're going to do is we're going to use a traditional memory error, such as a buffer out of bounds access, to change the target that needs to be executed. However, we're going to make sure that this use of that target is done during speculative execution. Okay. Now, what does that give us? Well, it first of all gives us the advantage that none of the Spectre mitigations work, because we've overwritten a function pointer, say a code pointer, using a memory error, using a buffer out of bounds read, which means that as far as speculative execution is concerned, it doesn't know who set that value, right? So it's, as far as speculative execution is concerned, that is actually the correct target. So let me illustrate this. Say we have our indirect call here, an indirect call to some computed address. Now, In speculative execution, what we would normally do in a Spectre attack is make sure that we set the target from the attacker's side in such a way that it will speculate, it will predict that it will execute some other code that the attacker controls. We don't do that. Instead, what we do is simply do the traditional software exploit, right? So the register is loaded from a value in memory, and we simply override that value, okay, with the value that we want to have executed, and then the indirect call will target that value. As far as speculative execution is concerned, whatever we write here is the right address. That is the address that needs to be executed. So speculative execution mitigations no longer work. The other thing that we get from this is that we make sure that this code is executed speculatively, and that means that we don't crash, right? So if you access some code that is some page that is not even mapped or that doesn't contain code, that's perfectly fine. The CPU is going to say, oops, I must have made a mistake during speculative execution. Let me rewind and continue at the right location. In other words, if we do this, we can do this branching of, using this indirect call to any address we want without ever crashing, okay? And while we do this, we can, again, just like in the blind drop attacks, look for side effects, different side effects in this particular case, but side effects still. And the side effects allow us to, for instance, find the code pages that contain the kernel image or the data pages, or we can even tell us very fine-grained things, such as particular snippets of code. And I'm just going to give you one example there where we can find an actual Spectre gadget. And once we have a Spectre gadget, we can read any byte from the kernel. Okay. So let me just explain how we're going to do this. We will take these two variants of Spectre that we saw earlier, variant 1 here and variant 2 here, and we kind of, marry them and not quite take, all the elements from both of them, but create this monstrosity that has some resemblance to both and has, shares some of the aspects. In particular, we take from Spectre variant 1 the idea that we can have a condition here that can be manipulated by the attacker such that it causes a misprediction and executes whatever is in the body speculatively. We don't care about this body anymore. We want something else to be executed, and what we want executed is instead one of these indirect branches that we recognize from Spectre variant 2. So we now can make sure that this code that we find here in the body is executed speculatively, okay? But we don't do anything with the branch predictor for this indirect call. Instead, we make sure that the function pointer, the pointer that is being used here, is corrupted using a traditional software attack. Okay. So let's have a look at an example, see what that means. And this is based on a vulnerability that existed in the Linux kernel in net/packet/afpacket.c. There was a write to an array element with an index that was attacker controlled and a value that was untrusted. So you could basically write to different values, not arbitrary, right? But you could write many places. And one of the things that you could write to, where you knew the location of, was a function pointer, because it was at a relative offset. Okay, so what you could do is overwrite the function pointer by manipulating the index, which was attacker controlled, and writing some value there. And here again, we wrote 41414141 as the address. Okay, so this makes the program, the kernel in this particular case, jump to whatever address we put in there. Okay. Normally, it will lead to a kernel crash, remember, and that would not be good. Okay, what happens if we overwrite this address with this, function pointer with this address, and it's being used? Well, it will lead to, if it's a valid address, it will lead to the instructions that are at that address to be loaded in the cache. Okay, so some bits in the address determine exactly where in the cache this will be loaded, which cache set. For instance, if this is the cache, maybe it says that the cache set 1285 will now contain the instructions corresponding to this address. Okay. We, as an attacker, are able to monitor this, to see that this is happening. Okay. The reason why we can see this is because we can execute also code that maps to the same cache set, right? So maybe we read from a number of cache lines in the same cache set, with the same bits that determine the same cache set, and we keep reading from this, keep reading from it, and it will be very fast, right? Because it will be in the cache until the kernel starts executing this code here, which also maps to the same cache set, which means that one of the cache lines of the attacker will be removed and that access will be slow. Okay, and the good news is that you can do this even if you're a user process and the code that you're monitoring is a kernel process. Okay, so because this cache is simply shared by user and kernel process. And what can we do with that? Well, the first really simple thing that we can do with that is probe for code pages, trying to find out which pages in the Linux kernel address space are code pages. And the thing is, the way to do that is really simple. Here we have our page, which contains this function pointer. We simply override the function pointer with a value, such as the value that we saw earlier, which maps to a particular cache set that we are monitoring from user space. Okay, so we as an attacker monitor this cache set, and if at some point it sees activity at that cache set, in other words, one of our accesses becomes slow, then we know with some probability, because it's always noisy, with some probability we know that this code was executed. Okay, so, and that will only happen if this was a valid code page. Okay, if we if we put a value in there, an address in there, that is the address of an unmapped page or a page that doesn't contain code, no instructions will be loaded in the cache. Okay, so we won't see activity. So now we find the code page, which is great because even on today's Linux, this is enough to leak the entire kernel address space. Okay, sorry, not the entire kernel address space, but at least the code. Because we can, if we know that this is a code page, we can try the page before that, see if that is also a code page, and the page before that, and see if that's a code page, and keep doing that until we hit something that is not a code page. And then we know the start, the base of the kernel image, and that also means that that we know the full kernel image. Okay, with coarse-grained address space layout randomization, you now know the entire kernel image. We can do more, however. We can also probe for data pages. Okay, so let's say we know that the kernel contains some code where some address on that page is used as a data pointer. So instructions such as this, we know that this exists in the kernel. So what we can do is corrupt not just this function pointer, but also put a value here, which is the same value that maps to the same cache set that we had earlier. So a value that maps to the same cache set, and then see whether or not this cache set gets activated. Then we know that this code, such code must have been executed. So in other words, we simply keep trying new values for the function pointer until we see activity in cache set 1285. And then we know that, oh, it must have found the right instructions, the corresponding instructions that use this value as a data pointer. And now we have the code pages, so the kernel image, and we have data pages. Okay, we don't really care which instructions we execute as long as it exhibits this sort of behavior, exhibits the cache activity in the appropriate place. I hope that is clear. Because now we get to the most complicated gadget, and that is, if we have this, we can do anything we want. We can leak all of the information from the Linux kernel, and it's a Spectre gadget. So remember, Spectre allows us to leak everything if we can operate it, if we can bypass all the Spectre mitigations. Well, we can bypass the Spectre mitigations because we're not looking for the actual speculative execution part of Spectre. We're looking only for these accesses now. So we're looking for instructions that look like this. It does an access with an untrusted index, and it uses whatever value it reads from for whatever value it reads as an index in a second array. Okay, let's have a look at what that might look like. Here we have again the memory layout where we have some pages, one page where we can corrupt things. We can corrupt the function pointer. We can also corrupt data there. We can corrupt a bunch of things. Okay. And then we have a data page, which we found earlier. We also have a page with known data. Okay, that's really easy. Once you know the kernel image, just adjacent to the kernel image, there's a page with all sorts of constants. So we know the data that are there. Okay, and for simplicity, I've just assumed that this memory location contains the value 10. Okay. So that's known data. This is data page. This is a page where we can corrupt things. And what we want to do is execute code that looks like this, right? So in instructions, for instance, the code might be doing this. So we take an index and dereference that and use whatever value you find there as an offset in this array. So if we write some index value here such that it accesses exactly, so we provide the address of this constant value, we know that the value in R0 will be 10, okay? And now we can provide the base of an address, and so a value for the base of the address, such that if we add 10 to that, it will lead to an access in cache set 1285 or whatever it is that the attacker is monitoring. So we manipulate index, we manipulate array, and then we start probing around with our function pointer until we see activity in cache set 1285. Okay, because then we know that we found a snippet of code like this. Okay, and that's great because once we have that, we can now provide a different value for the index and read different values from memory, okay, and leak all of the information in the Linux kernel. Okay, so let me just quickly give a demo. Here's Anis's machine, who was a PhD student who was doing this, and you can see that he was really called Anis. And he has a proof of concept running under his own user ID. And he starts running as an unprivileged user, he starts running this proof of concept attack code. And the first thing he will do is look for so-called last level cache eviction sets. Because remember, the attacker monitors the code by accessing the cache lines in that cache set. So he needs to find which cache sets are which addresses are the right addresses for these particular cache lines. Okay, eventually he finds those eviction sets, and then he starts looking for the kernel base address using the trick that I showed earlier, just looking for code pages and then walking down until you find the start of the kernel base. Okay, and once you have the kernel base, so you found the entire kernel image, the next thing he's doing is look for the heap address, so the start of the heap, which is also something called fizmap. I don't want to go into the details there, but this takes a while to keep probing for this, but eventually he finds it, and then once you know the kernel heap and the physical map, which is an area of memory which contains all of the mapping for all of the physical memory in the system. This is always part of the kernel. It also contains, therefore, all of the things that we as an attacker have put in memory in a particular page, so it needs to be there. So now we're going to look for a particular payload in a ROP payload, in other words. Now this takes a little bit longer, so let me just skip forward. Oh, That's very fast forward. Let me do that again. Now I'm no longer getting that. Just a second. Here we go. So still looking at this point, but eventually it will find the vulnerable buffer location. Let me just skip forward. And here we see that it did find it. And it's launched a traditional software exploit because now it's leaked all of the information from the Linux kernel that it needs for a traditional exploitation without any crashes. And you can see that Anis's POC gets root. And sure enough, if you now ask who you are, it turns out you're root, and indeed your user ID is 0, i.e. root. Okay, so let me just continue. This is just in case the demo didn't work. I could actually step you through this in a more gentle way. Let me skip towards the lessons that we learned from this. So the bad news. It turns out that the threat models that we used were limited. Okay. What we've assumed is that we can just attack Spectre against, traditional Spectre attacks where the user tampers with the branch predictor. We did not guard against the case where the target of the indirect branch, in this particular case, was manipulated using a traditional software attack. So our memory corruption attack, our traditional software attack, generalizes Spectre because we no longer need to use the wrong prediction to set a target address that the CPU is going to continue executing at in a speculative fashion. We can do that using memory corruption. And likewise, Spectre also generalizes these software attacks because we can now probe around, jump around without ever crashing because we do this speculatively. Okay. In other words, the combination is greater than the sum of its parts. And that's, like I said, bad news because we're used to dealing with vulnerabilities in a sort of like taxonomy as, initially discovered by Aristotle as a scientific method. We partition the world, right? So there's software vulnerabilities and there's hardware vulnerabilities. And the software vulnerabilities may be spatial memory errors, temporal memory errors. And the hardware vulnerabilities may be, I don't know, Spectre bugs or meltdown bugs or rowhammer bugs. And if we want to protect against these things, what we're going to do is focus on one particular branch in this taxonomy. We want to, guard against spatial memory errors as much as we can. And we want to guard maybe somebody else who's really good at this can guard against speculative execution attacks. But what we don't realize is that the attackers might actually combine these two. And therefore, we need to be aware at this level of what is going on at that level. And that makes it much harder to come up with good defenses. Okay, conclusions. To write secure code, that is kind of the message here. You need to know how everything that you do on this side interacts with everything that happens somewhere else in your system, in your taxonomy. And that is very difficult to do. This is not how software engineers are trained, right? So we try to have this separation of concerns as a guiding principle. We have abstractions that we can use and that we rely on, that we believe in, okay? And it turns out that these abstractions and separations of concern don't really work so well because attackers can and will combine these threat models. Now, this is one powerful illustration of this. I don't know of any other examples, but I think it's an interesting new class of attacks where you have completely different threat models combined. And in this case, the combination is even greater than the sum of its parts. If you want to know more about this, you can find the paper and also some additional information about this on our website, fusac.net. And if you're interested in some of our research, do follow us on Twitter. And with that, I've come to the end of my presentation, almost on time. It's 48 minutes, it seems. but hopefully there's still some time for questions. Thank you.
Perfect. Thanks for the great presentation. I'm happy to have some questions from the audience. You can directly unmute yourself and speak, or raise your hand, or use the chat.
Yeah.
Have an overview. Maybe people still need some time to understand and think through the things that you explained to come up with questions. In the meantime, not so much directly to this talk, but to the entire history of research. I don't know, many years ago it started with simple ROP that as return-oriented programming was completely new and was kind of a hype topic, and now it's a standard topic that we have that we teach in system security classes. How do you see this? Things that are getting more complex and needing more effort to teach, and kind of expanding field of how we should address this in terms of teaching this in general computer science, not only for security people, but like things that everyone should know. Every computer science students, we could do this easily, I don't know, 10 years ago, and now things get so much more complicated. So what's your view also as an author?
Yeah, that's an interesting. Yeah, that's an interesting question. So we see exactly the same things, right? So in the past, and that's not even so long ago, we thought any memory corruption attack in our master course, right? So we had a stack buffer overflow attack, and that was considered by ourselves as super advanced, right? We barely understood what we were doing at the time. It was super complicated. Can we even do this for the students? Nowadays, we teach not just these stack smashing attacks, these really simple stack smashing attacks, but even these really complicated return-oriented programming attacks, not in the master, but in the bachelor, right? So it seems that this devalues so quickly. And it also, it doesn't seem to become that much more complicated, although of course you need to know a little bit more about the computer systems, but it also seems that this knowledge sinks into the curriculum at a really rapid rate, right? So this attack, the transient execution attacks, the speculative execution attacks, were considered, magic when they were first published, right? So in 2018, everybody was trying to figure out how do they work. Now, nowadays, we teach them in our computer science curriculum also. And students, if you explain these things well, seem to have no real problems with it. In fact, the new edition of the Modern Operating Systems book has these speculative execution attacks as part of the regular textbook, right? So the chapter on security explains Spectre, explains Meltdown, and the principles behind them. It seems to very quickly go from super advanced to something that is accessible to every regular computer science student, which I think is a very worrying thing, because it also means that this becomes relatively easy to do in a year's time or 2 years' time, right? So something that is quantum physics when it comes out turns out to be regular Newtonian physics by the time your new book arrives. So that means that the attackers can also much more easily use this. I hope that answers your question. Yeah. So I think it's both interesting. So it's for the students, they learn a lot of super cool stuff very quickly, and it's also somewhat worrying because it means it's relatively easy to do at some point.
And we need to update our slides.
Yeah, that is actually a concern.
Excuse me. Okay. So any questions?
Yeah, I have a high-level question on your talk. So basically, you are telling us, which is fortunately very bad news, that the threat models kind of don't compose, nor architectural layers compose. And how do you think we should go away with it in the next like 10 or 20 years? Okay, now it's about, trying to specifically understand classes of attacks, trying to specifically come up with countermeasures. But do you believe there is space and need for a redesign of architectures? There are interesting papers popping up on contracts, for instance, right? To, put some rigorous assumptions across layers in a way that we can somehow break this kind of circle that you have shown in this talk. What's your take on that? Is it realistic? Should we go in this direction? Are there other ways? Are there actually ways to get around it?
Yeah. So yes, I think it is the right approach. The real question is whether or not this given the high performance system that we have today, whether it's realistic to redesign. So what you can do though is do this for new parts of a processor, right? So maybe a secure coprocessor which allows you to start anew, and where security really matters, and then you can use that for the most important things. And I do believe that the problem is caused by us using abstractions and layers that, and in other words, the interface between the contract between hardware and software that we've taken for granted, but that is insecure. There is an insecurity there, and this really needs to be addressed. And there is no other way to address it. We cannot expect a software engineer to be aware of all of the possible things that could possibly go wrong in the microarchitecture of your processor. Okay, so I believe that we train our software engineers out of necessity to rely on abstractions, to rely on encapsulating the complexity of the system that they're really using behind really nice libraries and APIs and so on, interfaces. But what we don't realize is that the abstractions, or what many people don't realize, is that these abstractions are leaky, right? So we may think that this encapsulates the behavior of the hardware or the kernel or some really complex code. But in reality, there are interactions between the code that we write as a software engineer and the code that runs in the firmware of your CPU, or the way the memory is being used. The rowhammer vulnerability is another example of these things. So we hide things, and by hiding these things, we actually hide some of the insecurities that the vulnerabilities that are there, which are in the cracks in those abstractions, in those layers. I hope that answers your question. But I do think that the hardware software contract work that we see is, I think, super good, and it's certainly for new areas. So you're not going to compete with your x86 64 systems that are designed for performance, and they're not going to do away with all of these super cool optimizations that make your code run fast. But there is a lot of other stuff that we're currently designing where this might be possible. Yeah, so we're looking at some of these hardware things that we could do to make it more secure. Okay, so then there was a comment, I guess. Haste, which is a Black Hat talk from 2016. Okay, yeah, I would have to look at that, Marco. I don't quite know what that attack does. Yeah, but yeah, it may well be that there are others like it. So what we're used to seeing, right, is combinations of attack vectors. So this is not uncommon. We use one vulnerability, for instance, to break address space layout randomization. right? So we've had attacks that use the cache side channel to break address space layout randomization. We've had other vulnerabilities that are used to break address space layout randomization. So sometimes hardware vulnerabilities, right? And then followed by that, we have traditional software exploits. What makes this attack, it's called blindside. What makes blindside a little bit different, I think, is that here we have not just one thing followed by another, but it's actually, you need these two together and they make each other stronger. So that is what I refer to as symbiotic. And it may well be that this attack that you're referring to has that same property, but most of the combination of different threat vectors, attack vectors, threat models is a sequential combination, rather than you really need to apply them together and you can do things that would otherwise not be possible. So I'll look at this presentation right after this discussion is over. Okay, good. Any other questions?
I think I don't see any additional questions right now. So thanks for the great presentation.